My name is Dr. Esther Trufan, and in this video, we're going to explore the reaction of magnesium ribbon with a fairly concentrated or 3 molar solution of hydrochloric acid. For this reaction, then, we're going to use magnesium ribbon and a 3 molar hydrochloric acid solution. Because we are going to measure both the volume of the generated hydrogen gas and the heat generated from this solution, we're going to set it up both as a thermochemistry experiment and as a gas formation experiment. Because it will be a gas forming reaction, we want to collect the amount of gas formed. For that, we're going to use a bin that has been filled with water, and we're going to measure the temperature of the water in a little bit. To do that, we're going to use a thermometer. Then we are going to collect the volume of the generated gas. We're going to use a 100 milliliter graduated cylinder. We are going to add a known amount of hydrochloric acid solution, and that is going to be about 5 milliliters. So we need a 10 milliliter graduated cylinder. We're going to generate the gas and transfer it. So we will be using a large test tube that will be capped by a rubber septa that is connected through a rubber tubing, which will go under the graduated cylinder. And then, because we're also treating it as a thermochemistry experiment and we want to capture the amount of heat generated, we are going to use a nestled styrofoam cup. It will be capped by a cardboard piece, and I created 2 holes. One, a large one that will fit the large test tube, it will slide right through it, and a smaller one that will be used for the thermometer. And we want to make sure that the 2 holes, the larger and the smaller hole, will both fit on top of the calorimeter or the 2 coffee cups. Because we want to know the amount of heat that was generated in the reaction, we're going to add some water, and that will be approximately 50 milliliters, just enough to cover the area that will have the hydrochloric acid in the large test tube. So it will be just a little bit on the bottom. Because we're adding water, we will use some deionized water just to make sure that the specific heat of it is consistent with reported literature values. And to make any adjustments on my measurements, I will be using a pipette with a bulb. Because we want to know how much water we're using in the calorimeter, we're also going to use a scale. And here I have that. Now let's get started. First, let's prep for our gas forming reaction. For that, we're going to take our 100 milliliter graduated cylinder. And because it has this solid top, we're going to remove it because we want to make sure that there will be no air bubbles and we can't see through a solid bottom. So we'll open it up. Then we're going to add water until it is full to the brim. And we don't want any bubbles inside. When it is full to the brim, we can cover it with our hand or with our gloves. And then we turn it upside down and we slide it under the water, and then we'll let it go. And if we did it well, we shouldn't see any gas bubbles coming to the top. If we want to, we can add the solid top back, but it's not important. We can let it gently rest on the side and we can wipe our hands before we move on to the next step. So now for the next part of our experiment, we're going to take our tubing and we're going to slide it through the water under our graduated cylinder, and we're going to try to make sure that it doesn't come out. And now we have done everything we needed to do to collect the gas. Let's prepare for the heat measurements next. We're going to take our scale, turn it on. When it shows 0.00, we place our styrofoam cup on top. We tare it. It will show 0.00. At this point, we will measure 50 milliliters of deionized water. We're using the 50 milliliter graduated cylinder, and we want to make sure that we are under the 50 milliliter mark. And we have 49.2 milliliters. We pour it into our styrofoam cup. We measure the mass of the water and we record it as such. It is 49.26 grams. With that, we're done. We can set our scale to the side. Now we prepare our experiment. We take our large test tube and we can place it in the water. We take our 10 milliliter graduated cylinder and we measure into it approximately 5 milliliters of the 3 molar hydrochloric acid solution. we are at 5.03 milliliters. I'm going to take my hydrochloric acid solution and try to pour it into my large test tube so that it doesn't touch the sides of my test tube. Once it is completely transferred, we are almost ready to get started. First, we're going to take our cardboard lid, slide our large test tube through it so that the test tube touches the bottom of our styrofoam cup. We're going to slide our thermometer so it goes all the way to the bottom. And we're going to record the starting temperature of our water. If we need to raise it a little bit, we can. It's likely going to be very close to room temperature. It is 21.1 degrees Celsius. And with that, we have our mass of water, the starting temperature of the water. We can look up the specific heat of water, and we will find out the end temperature of the water once the reaction is complete. Now to get our reaction started, we're going to slightly angle our test tube, get our magnesium ribbon. And because I wanted to get my magnesium ribbon more accurately measured than 2 decimal places, I actually used an analytical scale and measured 0.0721 grams of a magnesium ribbon. And it's right here. I transferred it so I would have it separate. When the magnesium ribbon slides into the test tube, I will very quickly put the rubber septum on top, and then the reaction will begin. We can do a quick countdown in our heads. 1, 2, 3. And we're going to see the gas forming in the 100 milliliter graduated cylinder that was connected to the rubber tubing. And if there is any heat generated, we will capture it through our thermometer. Because we can't see inside the reaction vessel as if we were just doing this as a gas forming reaction, the only way to tell if our reaction is complete is by the hydrogen gas formation slowing and eventually stopping. We still see a couple bubbles coming up. We can gently move it around, but we want to make sure that the shaking doesn't pull the rubber tubing from under the graduated cylinder. And it appears the hydrogen gas formation ceased. At this point, we need to record 2 more temperatures. The temperature at the end from inside the calorimeter, and then we also have to record the temperature of our water bath, which will be the same as the temperature of the hydrogen gas that was collected above it. So we need the temperature of the water bath for our gas loss calculation, and we will need the temperature at the end of our water from the coffee cup calorimeter for our thermochemistry calculation. So let's gently lift it up, and we find that our final temperature is 26.0 degrees Celsius, which is not a massive change, but remember, we've done this reaction at a fairly small scale. And just to confirm that our reaction is complete, we can pull it out, and we see that it's a clear solution, which means that all the magnesium ribbon we placed inside has been consumed. We can remove the rubber stopper and set our large test tube to the side. We take our thermometer and we're going to place it inside the water bath for about 20 to 30 seconds and then record the temperature of the water bath. It is 20.5 degrees Celsius. Next, before we do anything else, we are going to remove the rubber tubing from under the graduated cylinder. And as long as we keep the top of the graduated cylinder submerged underwater, it will not release the water. Then we're going to record the volume of our gas in the graduated cylinder, and this will be the volume of the hydrogen gas collected. So we slide to eye level and we record our volume. It is 68.9 milliliters. We have the temperature of our water, which is the same as the temperature of the gas. We have the volume of our gas that was collected above water. We know the amount of magnesium that we started with and the amount of hydrochloric acid, both concentration and volume. And from that, we will be able to do all the calculations related to the gas loss component of this reaction. Because we know the starting temperature and the end temperature of our water from the calorimeter, we will be able to determine how much heat was released by the reaction. And once we have the heat released from the reaction, we will be able to also determine the enthalpy per mole of the reaction.